Ladies and gentlemen, so good afternoon. It's my great pleasure and honor to be here. I mean, I'm on an official delegation from the Scientific Criminal Science within the Lawyer Society for only 3 days. So I actually came today. Cambridge is actually for the lunch meet with the widow of my former supervisor, Michael Power. I thank Professor Chen for his kind invitation to give a short talk here. So I didn't prepare well because I was on traveling. I didn't expect to give an academic talk, but so I will talk to you about a small work earlier this year I have done. So it's about the BB method. So the outline of the talk will be I will give a brief introduction about the BB method. Then I will talk before I talk about the monotone property. I will first of all to talk about the non-monotone property of the method. Then I go to the monotone properties of the BB method. And finally will be a discussion. So I know the program Professor Chen is running about image processing, which I know nothing about. I don't know image, but I know images. You have to minimize some object functions. So I myself am doing numerical method for optimization. So about the theoretical property of famous algorithm like quasi-Newton trust region nonlinear conjugate gradient method. So, but today the method I talk about is actually about the gradient method. Gradient method actually is the simplest method for optimization, which namely every iteration you move the counter iteration along the negative gradient direction. So think about your kind of the mountain, you're just going the steepest descent, direction, trying to higher. So that is very, intuitively is very straightforward method. You're always searching along the gradient method and the gradient direction. So rough saying the iteration will have very simple form, xk plus 1 will be xk, move along the direction of the negative gradient, and you have a step size. Of course, all the gradient methods are in the same framework. So the only difference is how you choose the alpha k. So the step size, the different way of choosing step size is very important. Particularly for machine learning problem nowadays, people for big data problem, you have large scale problem. For example, for machine learning problem, which is basically mathematically it's the sum of many terms of function. You cannot afford to compute every term of them. You choose one of them, which is stochastic gradient, doing these kind of things. But for this kind of algorithm, people have to choose a very conservative step, namely choose a very small step size to make sure you always get a reduced function. So now, of course, the gradient method, this type of method is, as I said, is the most simple type of method. And of course, if you choose a small step, you're sure you can always reduce the function by a little bit. Then that means you're sure the method is robust. You can use. And also, of course, because it doesn't use any fancy secondary information like a quasi-Newton, limited memory VFGs, and conjugate gradient, you require very small storage, and which is very suitable for large-scale problems. So now, as I said, the only difference is about how to choose step size. So an obvious one way of choosing step size is what we call the exact line search, which is also a method called steepest descent method, where you choose a step size to make the function as small as possible. So that means you minimize the function in n dimension. So in each iteration, you're searching the gradient direction. Now you reduce to the one dimension problem. So you minimize the function along this one dimension, then you get the next iteration point. So that is a trivial way of doing it. So this is, of course, for fixed step size, you make sure you can reduce function. Normally you require the step size will be upper bounded by 1 over the upper bound for the Lipschitz constant of the gradients. So that is L, which is this, and this. So, of course, the converge of the steepest method is linear. Even you have a convex quadratic function, which is simple case, you minimize the convex quadratic function, use a steepest method, you can prove the conversion rate is linear, and also the fraction you will get to reduce, it depends on the condition number of the function, namely the condition number is defined the largest eigenvalue divided by the smallest eigenvalue of the second order matrix, second order difference of the object function. So if the function is with your condition, namely this couple, the condition number will be very, very large, then you can show this is a couple minus 1 divided by minus plus 1 will be very, very close to 1. So that means conversion. Even though it's a linear conversion, but it's very, very close to very, very slow conversion. So this is also observed in numerical experiments. So if you run between the quadratic function, you try the steepest descent method, the method is very, very slow. This is very, think about the steepest method is you search along the steepest direction, and then at the next iteration, you change 90 degrees. So if the function is very, your condition will be, you will have a zigzag. So this is very intuitive, is very slow algorithm. So that's why, steepest method, even though it's always in the first chapter of any optimization textbook, but after the first chapter, nobody will discuss about this method. I'm saying, hey, this is not a good method, even though the engineering like this method because it's easy to implement and reliable, as I said. But for mathematician, we say this is bad guy because you have very slow conversion and you can do nothing for the mathematics. It's only linear, and the linear rate is very close to 1 when the condition is very, very worse your condition. So this is the picture. Very simple examples. You give a function which is a very simple function. This function has the contour line which is ellipsoid. The longer axis and the short axis, the ratio is 10 to 1. So it's not that bad condition problem. But if you iterate from starting from x equals to 1, y equals to 100, then after 20 iteration, so you can see you only go, suppose the optimization, the minimize the function is here and stand here. After 20 iteration, you only go about 1/3. So that means it's very, very slow. After 20 iteration, you only reduce the error 1, 2, 3. So it's a very slow algorithm, as I said. But the method I'm going to discuss today is called the BB method, or Barzilai-Borwein. Professor Chen asked me, who are those guys? So Borwein is a famous mathematician. Unfortunately, he passed away about 2 years ago at the age of 61 or something like that. So he's very, very, very young. He was the president of the Canadian Mathematical Society. He is not only for doing optimization, he is a kind of a polymath person. So he has done a lot of other mathematical research. For example, he used to be the world champion for computing pi for up to the, I think, 2 billion digits or something like that. Of course, he has done a lot of other mathematical results. So one day, somehow, he was interested about the grading method. Why the grading method is not good? This is a paper, I think, he wrote with his PhD student, Barzilai. I was very fortunate because I was one of the referees for the paper, so I know the method really firsthand. So the idea is very simple. For those who know BB method, you know the formula. But for those who don't know, I will use a simpler language to explain. Basically, what is the steepest method? Steepest method is you're going along the grading method, the grading direction. For example, you have to go along this direction, the best step size, which is say 2 meters, you go to here. Then you change 90 degrees. So along the direction, you go to the best step size, which is 3 meters. But BB method don't do this way. So he computed 2 meters. He used in the next iteration. So you can think about a guy who is, a delayed thinking. It compute step size, but keep it used for the next iteration. So in this iteration, it should be 3 meters, I go to the next one. So it's some kind of like the optimal step size you keep for the next iteration. So I was joking, when I lecture optimization lectures, I always joking the best boy in the class should not find the best girl in the same class, but you have to find the best girl in the lower class, something like that, lower grade. So that is the idea. But of course, the mathematical idea behind this formula is actually use some kind of quasi-Newton information. So I'm not explain in detail. So this is the original paper called Barzilai-Borwein 1988, I think. So if you apply the BP step for the same problem, which I showed you the picture about a couple minutes ago, the same function, starting from the same iteration point, starting point. So after 1, 2, 3, 4, 5, 6, 7, 8, 9, and after 9 iteration, you will find the exact minima. So it's amazingly faster. And I mean, this is only for a 2-dimensional problem, which have this formula. But even applied to higher dimension problem, we also observe, I mean, the BB method behave very, very good. And this is, the paper of this BB's paper has, I think, give us a lot of interest or exciting, a lot of people to doing about the gradient method. For example, like Roger Fletcher's also one of the fellow for the society also, unfortunately, he also passed away a couple of years ago. I think last 2 years, not good years for optimization or community. And so that stimulates a lot of research on the BB method, particularly for converge, for not only for quadratic function, but also for convex functions, how we extend it, and also general, because it originally Barzilai-Borwein paper, they study for n equal to 2 and they get some kind of interesting result. So the talk I'm going to give today is actually also what I call is last question of Michael Power, my PhD advisor. So at one of the conference, when people talk about the BB method is so good, BB method has one undesired property, which is a non-monotone. Look at the picture. I will show you the previous picture here. So you can look here, starting here, and then this point will be certainly jump to here. So look at it here, x is equal to 10, and y is equal to the same thing. But this point now, x minus 70, so that means it's non-monotone. So the function will be increasing. So you're trying to minimize the function, but if you record all the iterations, the BB method access, and some of the iteration will be allow the function to increase. So this is the property which we call undesirable property because it's a non-monotone. Of course, for quadratic function, even though it is a non-monotone, we can prove eventually it will converge, so no problem. But if we try to extend the idea to general non-linear function, that is not so trivial. So that making the BB method is not so trivial to extend it to other class of function. So, but for quadratic function, we know it is convergent. So Mike Power, at one of the conference when people talk about BB method, so he asked a very interesting question. BB method is not monotone for the object function, nor is not monotone for the residual of the gradient. Whether it is possible, we can prove this method is monotone to something else. So that is his original question. So after talking, he just raised his hand and asked a question. This picture was taken, I think, only a few months before his death when he gets a talk in Beijing. So this is the talk today is trying to answer his questions, but of course we have not yet get a completely solution to his question, but partially solution to his questions. So that is the talk, the content of the talk. So now I'll go to the technical details about. First of all, we look at the non-monotone property of the BB method. So numerical results, we show, you just program the algorithm, apply it to any randomly chosen quadratic convex function, and you'll find the function value is not monotone, the residual of the gradient which is a monotone. Of course, when we try to minimize the function, we try to judge in the point whether it's good or bad by compare the objective function value f of x. Or we can also try to evaluate the residual to gradient, because once the gradient equals 0, we say we get the optimal point. So that is two of the criteria people are thinking how good the iteration point it is. Of course, if you look at the objective function, how far it is away from objective the optimal objective function, you can write it down. You can look at this which you expanded the function by Taylor expansion at the optimal solution. That will be, you can write it down, is also some kind of quadratic form of depends on the gradient residual. So that means no matter the objective function f of x or the residual of the gradient, either of them or both of them can be regarded as some kind of norm or weighted norm of the gradient. So that means, so what I'm trying to say, so no matter the function value or the gradient value, we can always thinking it's kind of a W norm of the G. So if look at the gradient norm, which is W equal to I, and of course it's the function value, which is W equal to the inverse of the second order derivative of the objective function. So the first question we have to ask, whether it is possible, if we're clever enough to choose a very good W to make it the monotone for the VB method, then you can prove convergence. Okay, but unfortunately, I will not go into detail. I mean, I only go with the conclusion. So after our analysis of the originally VB method based on the similar technique of by Barzilai-Borwein, I mean, to study the function value in the very simple case with n equal to 2, and we're able to end up. So that it means for any W we prove it is not possible to prove monotone for this kind of function. So that means if for any positive definite matrix W, you define this norm, so I can show you then it is impossible to give a monotone result. So that means we get a negative answer to Paul's question. So for this specific norm or type of norm, if the norm is defined by a fixed matrix W, then there is no hope to establish any monotone result. So this is the negative result. So now I also trying to also give you some, I mean, positive results. I mean, we have to be optimistic, otherwise we will be hung ourselves not doing research. So now I try to give you some optimistic results about, we're also able to get some very, I mean, initial results about some of the monotone property of the method. So now look at the VB step, which is defined by the step size, which is roughly is the second curvature of the function in the previous iteration. So because we're also assuming the function is a convex quadratic function, which is a simple case, then the alpha k can be easily computed by this formula. Because we're given a theoretic study of the algorithm, so it really doesn't matter. We can assume in the function H is a diagonal matrix. You just by changing the basis of the variable, I mean doing some of the orthogonal transformation of the variable, then we can assume this H, the function is a diagonal positive definite matrices. So in that case, we're able to write down the recursive relation between of the gradients. So look at write the gradients which have the n component. Then each of the component is also dependent by this, which is each iteration. So each component have their own iteration form. Then we can easily give the upper bound of how each component will be reduced, and we are able to show you the first component will be always getting less and less. So the trouble why give as a non-monotone because the late component can be getting enlarged. So that is the first neighborhood you can easily compute. Then what we can do, so based on these results, as I said, this will be always with the so if the lambda n minus divided by lambda 1, of course this will be greater than 1. But if this guy is less than 2, then 1 minus this guy will be always have a absolutely less than 1. So that means for the special case, if the condition number of the function is not too large, then both of these will be monotone. So this is the very trivial result. Not really need a mathematical analysis. Any student can see this. So that means we know for the condition number is not large. So then we know the BB method will be monotone. So that means if people have ear condition problem and you do pre-process by pre-scaling, then you can make some, the problem is a good condition, then you will always get a monotone algorithm. That means even though the original method is not monotone, but it is applied to a good condition problem, it will be monotone. So that's why precondition is important for always for optimization. No matter once, if you could do precondition, if you know how to do precondition, you're encouraged to try to do precondition before you do the minimization. So now I will do to further now for the case what we do if we don't assume any of the condition number for the function, what we could do. So one result we proved the monotone is based on the like the alpha beta order of the gradient component. So look at the gradient function, the gradient which G1, G2, and G3, which is right at the n component of the gradient. And if you look at these, if think about the you look at the dictionary, the dictional order, then we were able to prove if we, based on this dictional order, this will be monotone. So I'm not showing you how you prove the results, but only give the results. So what I'm trying to say, the monotone is, of course. Now I didn't assume H is at the diagonal matrices. So if H is a positive definite matrix which have the orthogonal decomposition in this form. So that means it will be always based on this decomposition form. It will be monotone based on the dictional order. So think about if you assume H is a diagonal matrix, the Q will be I. That is the gradient itself. So that means if you orthogonally transform the problem based on to make the problem into a diagonal second order term, then in that basis, the gradient component will be monotone if the monotone definition is based on the dictional order. So this is the first result. So this is the encouraging result. And this kind of monotone can be used to prove the convergence. Why? Because, for example, you're thinking about you have a word is a monotone. So if A, so the second word, it has to be A, or back then smaller than A will be B or C. So you will be proved the first alpha beta have to go to Z. Then once this convergence, because it's still going to converge, now you can prove the second character also will be go to convergence. So in this way, you can prove the convergence result, by iterative way. So now, what I'm saying, this is what they call the field property of the BB method. So another sense is, look at this as the function residual and also the step size. So I compare these two. The way why I combine these two is I know because BB method is used the best step size in the previous iteration. So I know if this is equal to the previous, then it will be reduced to the steepest and will be monotone. So if this is not monotone, means your steps is too large. So that means I think one of these have to reduce. So I define this, what I call the filter method. It's also Roger Fletcher was one of the expert on the filter method. So I was able to show in this. So either this, the function residual will be reduced, or the step size compared with the previous one always will be reduced. So each of these either will be reduced. So that is the idea of proofs like that. So what I'm trying to say, if this alpha either it's in this region the function reduced, if the alpha is outside, then I see this side, the ratio between alpha k divided by x1 all will be reduced. So either of these will be reduced. That is the filter approach. So think about it, you compare apples, either it's bigger or it's more redder, I may think, something like that. So each one of the factors will be reduced. So I think I will skip the detail. I mean, this is a very simple mathematical analysis. I'm not boring you, but I hope you trust me to my induction to character. So the two Ks you can either will be reduced. So a lot of things is doing this, and also I have to study further for the n equal to 2 case. I have assuming the two lambda is not equal. Of course, that is the standard assumption. Otherwise, if you have to the two eigenvalue of the Hessian is the same, then you will end up after two iterations will get the minimizer. So what I have done is also saying if, as I said, the first component will be always get reduced. It won't give you any trouble. So only what we worry is about the second component of the gradients. So this lemma, what I call the key lemma, which is essential for the theoretical analysis, if the second component is increasing by this factor, I will be able to show the second component will be reduced significantly compared with the first component in previous iteration. Remember, this first guy, this guy is a guy will be converged to 0 because it's a monotone. So that means either this will be reduced or the previous iteration will be very, very small. So that means I have two components. So what I try either this component will be reduced by a fraction. If this is not the case, then in the two iteration before, k minus 1, the one will be very, very small. So this is the kind of idea making this the lemma important to give you some kind of monotone. So even though I'm not able to prove each iteration will be monotone, but I will say if in one iteration is not monotone reduced, but the previous one will be very, very small because it's monotone compared, it will be small with smaller than the first component. But the first component is already a monotone sequence. So that means I can prove the second sequence either itself in the category is monotone, or two iterations before it is smaller or majorized by the first sequence, which is monotone. So that means, I can either prove, if I try to prove I'm getting better and better, either I can prove today I will getting better than yesterday, or if not, I can prove 2 days ago myself is better than a good guy, which is every day is improving, something like that. So that is a very interesting observation, I think. I mean, I'm not getting in detail. Doing this, I mean now, because as I said, the two sequence is very detailed, not easy to explain, but I managed to define a scalar which is kind of a strange norm you can think about it, which is the kind of combination of the first component the second component, but those are constants which I have to using for making the theory looks very nicer. So that the pi they pay in this 5K, the definition is not, looks not that beautiful, but anyhow, that is my definition. It's kind of what I call the scale infinite norm. Infinite norm is the maximum of two of them. So if we define this guy, this is kind of interesting norm, because think about, look at the actually for the xk minus the x star, which is solution, define the infinite norm. It's actually this guy is like that. So you compare these two guys. So this is very kind of very nice approximation to this infinite norm. So this is what I think is I use a very good name for this called a scaled infinite norm. So having done this, I was able to prove this is what I call the two-step monotone. This will be always less. The maximum this to prove is 2 times this is a fraction which is smaller than 1. So that is the monotone result. So that means I define a special norm of the gradient, and this guy will be monotone if I compare not exactly. I'm not reducing by myself, but by yesterday and the day before yesterday, the maximum things will be reduced. So if we define the maximum of these two guys as one guy, and this guy will be monotonely decreasing by linearly and converging linearly. I will not go into the detail of the proof. If any of you want to know, send me an email. I can send you the slide. I can just slide already Professor Sen's notebook. So that's what I'm trying to say. So if you define a metric function like that, then this metric function will be satisfied for any of these, will be always monotone decreasing, but every 2 iterations it will be reduced by at least a fraction of the two iterations ago, and this guy is more than 1. So you can prove linear conversion of the sequence, but also monotone. So this is last slide of mine. So I want to, in the end, I want to summarize. So what I have done is for any positive definite image W, you define the norm like GK transfer W GK. This is in this type of norm, there is no hope to prove monotone for the BB method. So that means if we fix and you define the metric function, which is what I call it is a quadratic function. So if you have original function is quadratic. So you define the quadratic function which is based on the current iteration. There is no hope for you to prove any monotone result. So look at the definition of what I define this phi. So I prove use some kind of introduce a special metric function. Then I was able to prove the monotone. And also think about the field property. So you think about this to so that is the quadratic. This is also a fraction. So what I'm trying to say is even this in the dictionary order and also in the field philosophy, you can get some kind of monotone result. So this is the currently we have done. But what I want to not have yet done is, because the current result is I using the very special case for n equal to 2. So if we a greater than 2, whether the same metric function will be monotone or not is not that trivial. Another sense is about the metric function we have defined is like what I call is a scaled infinity norm. As I said, 2 norm, there is no hope. And for infinity norm, but it's a scale, it is possible. But what is possible to think about, because look at this field term. So I have, looks very likely if this is not reduced, this will be reduced. So I have compared the order of these. So basically this and the square of this is more or less in the same order. So if you either this will reduce by certain sense, if this also reduce. So there might be a possibility to prove the monotone of this guy. So now you have a quadratic function. This is the cube, the polynomial of fourth order divided by large polynomial of fourth order. So like a rational function. So think about, as I said, Powers conjunction, whether you can able to find a norm or matter function to make it a monotone. As I said, the quadratic is not. So maybe rational function, it might be possible. So you have to define a matter function which is rely on the original object function, but you have to think about maybe higher order polynomial or rational function. So that is kind of, I think, is possible we could do more theoretical result in this direction. So I think that's my talk. Thanks very much for your attention. Okay.
Any questions?
Okay.
Max?
Okay.
So the BB step using scalar to approximate the Hessian
Yeah.
In an L2 sense.
What?
In the L2 sense, least square.
Yeah.
So is it possible to using other criteria other than least square?
Least square? Yeah, I think it is possible, but what I'm trying to say, because the BB step, even you use all these kind of like least square or other kind of two norm, you cannot get the monotone. So that's why. So now looks to me the infinity norm is better, I think. So maybe like that's why, I mean, for image people are like the infinite norm or one norm, this kind of long smooth norm. The two norm which is smooth, but because the monotone nature of the BB, so if you choose the very smooth norm, you have low hope to get the monotone. But maybe, I mean, people don't care about the monotone as long as you in the end you can get the good solution. Okay, but my talk is more theoretical to study the property whether you can show to get the monotone, because really we're trying to understand it mathematically, even though you're not monotone, but if you change in the other energy space, it will be monotone. Yeah, that's my good question.
Another question.
Yeah, okay. Mm-hmm.
So can I say this? The non-monotonic property is because that the scalar approximation of the Hessian is not good enough.
I think yes or no. Yes is because, of course, because the Hessian information they use is in the previous iteration. So even though you use a very good approximation in the previous iteration, but if you apply to this iteration, you give it the error. So that's making it non-monotone. So that's why I say it's twofold. Yeah, good question. Yeah, thank you.
Sorry. So if yes, yes.
I mean, because namely BB idea is I don't have separate information in the counter iteration, in the counter direction. So think about I trying to climb a mountain in this direction. So I know the slope of the mountain, but I don't know the curvature of this direction. But I have been climbed the mountain from here to here, so I know the curvature in this direction. So BB idea is use the curvature in this direction to guide me how far away in this direction. So that is the error, I think.
Yep. But what if we use a diagonal matrix instead of a scalar to?
Yeah, that is a very good question. I mean, this is nowadays for gradient method. There is a tendency of research on also in application, because BB method or gradient method is use a scalar matrices. I mean, you can choose a different scalar times identity matrix to approximation. So there may be to choosing a diagonal matrix which allow all the n components are not the same. That will be, I think, it's a broader method. So basically, you have a lot of different choice. I think, of course, there should be. I think we'll be needing to better method, of course, because you make all of them are the same. It's like a special case, of course. The general case, of course, give you a lot of room to improve. I think it's also a direction worth to research, particularly for large scale problem. Not only, I mean, maybe you're not so ambitious to make all the n component change, but you maybe allow 5 or 10 of them out of the 1,000 by randomly allow them have a different choice will become a good choice. Yeah, good question, I think, also worth to study. Very good question.
Any other comments?
So your original BB method
Yeah.
doesn't require second order derivative. It's just approximation. It only requires something like C1 function, C1 convex or something. Is that right?
Uh-huh.
But in your proof, you assumed the function to be essentially a quadratic form, a quadratic function itself. Then if you require all the eigenvalues in general of the Hessian
Yeah.
and the rotation, then you can just write down the solution by take the inverse. That's the end of the solution. the thing. If you require all the information, which if you have, you can find the inverse of h, then you solve the equation. Oh, you take the gradient.
Yeah, yeah.
Find the stationary
Yeah.
if you have all of those already.
It's only for
Yeah.
linear problem, for the
Yeah.
quadratic problem.
Yeah, that's the quadratic.
Yeah.
The theorem is for the quadratic. But if you require all of those, then you already solve it exactly, right? So I just don't know whether you can avoid using such information just to go ahead.
But I think this
Yeah.
is not part of the method,
Yeah.
it's the analysis
Yeah.
part.
Yeah.
Okay, so
Yeah. Professor
Yeah.
Zheng could understand the question provided.
Yeah.
Always assume this lambda 1, lambda 2 is for theoretical analysis. In the
Okay.
computation, we don't use. So that
Okay,
means
yes.
the algorithm, we don't know you have. I mean, those lambda appear in the paper, it's showing for you to make the analysis. So it's not used by the algorithm. So for the algorithm BB method, they don't use second order derivative. They only use first order. But we have to know if we understand the problem, understand how to behave of the algorithm, I have to make sure, even for this very special case, how it will behave. So it's only for theoretical analysis, it's not for computational
Can we have a
implementation.
look at your first slide, see
Yeah.
the BP method?
Yeah, yeah.
You got alpha 1,
Yeah.
alpha 2,
Yeah. You can
To
look
see
at
how it
the-
works at the beginning.
Yeah, the beginning.
Near somewhere, the method.
Yeah.
Right here.
So that is,
How do we use the alpha?
yeah, that is the algorithm. So you only use alpha. They have two versions of the BB, but they use S and Y. S is actually the difference of the value, and so that is all you use. I mean, computationally. All the later the theory, the lemma I use is for the analysis. So how it will behave.
So, my question is, with this alpha choice,
Yeah.
S, Y, K,
Yeah.
how do you update the new iterate? How do you update?
So you every time, for example, at the counter iteration,
Okay,
assume you have the previous xk minus 1.
okay,
So you have done this.
yeah,
So you can choose the alpha. So once you have the alpha, then of course you can get the next xk plus 1.
oh, you still
Yeah.
use the search.
Yeah, you still
search
use the
direction.
gradient. Yeah, you still use the same gradient. So
Oh,
as I said,
yeah,
the BB
right.
method is always a gradient.
Oh, I see, yeah.
That's the only way you choose the alpha,
Alpha,
have
I
a
see.
specific formula.
That's interesting.
So
But you do it twice.
yeah. So you do this.
Oh, I see.
So every time you just compute one gradient. So only there's a step difference. Yeah.
What is the rate of convergence for such a
Very good question. Because,
refined choice
Yeah,
of alpha k?
very good question. But this I didn't mention for the at the talk. For the BB method, as I said, for the steepest method,
Yeah.
you only can prove linear conversion.
Yeah.
But for the BB step, for n equal to 2, you can prove superlinear conversion. That is amazing. People never thought of this. For n equal to 2, this method, you can prove superlinear conversion. And what even surprising is the superlinear conversion is really getting better and better if the function is EL and EL condition. So that means you have a large condition number, the BB method will converge quicker. That is amazing. So
That's right.
that is surprising. Yeah. That is the original 88 paper that want to prove this.
So for this convergence theorem,
Yeah.
you need F to be, say, C11 or something like that.
Of course, no, I mean, the theoretical, yeah.
You need to
Yeah.
emphasize.
Actually, I mean, the original result, when we prove, is supposing the function is quadratic. So, because optimization people is always like that. When you're near the solution, when you're converging, first of all, we prove the method is converging. When you're converging, when we need to prove the superlinear conversion, then we have to assume the function is I mean, second order differential at the solution, near the solution. Because even Newton's method, if you don't have second order smooth, because the idea of method, if the method is quick, we think the Newton's method is always a good method. Think about the Newton. Newton have to use second order derivative. I mean, even though the method we don't compute the second order method, but the method must be, the function must behave very nicely. So if we have this belief, so at the solution, near the solution, we replace the function by the quadratic approximation. We throw away the higher order error, then roughly doing the same thing. So that's why when we prove analysis, locally we assume the function is quadratic. That is the reason. Okay. For general non-convex function or non-quadratic function, they don't have these kind of results. Because, as I said, the BB method, which is non-monotone, even for the global conversion, we cannot prove. So even for the, you just apply a general convex function, you use the BB step, I mean, mathematician can always build counter-example, make the argument cycle. Yeah. So, because mathematician too clever.
So in the situation
Yeah.
of non-smooth
Yeah.
convex, like what Nesterov
Yeah,
looked at.
Yeah, they don't, the BB step don't have this kind of.
He usually first smooths the thing a bit.
Yeah, this is for smooth.
Yeah, then you start to iterate.
Yeah.
So it's applied. This method applies to the smooth version.
Yeah.
Because I think there are other sort of people. One is this Moreau envelope approach, like Chabot, to do the primordial thing.
Yeah.
Essentially calculate along the Moreau envelope rather than the original non-smooth function to do things. I don't know what the question should be. Whether this thing can be adopted to this kind of situation.
Yeah, I know what you mean. I know what you mean because nowadays, particularly for image problem, I mean, people using like L1, I mean, minimization. They have a lot of like a cone shape functions. I mean, this is spatial non-smooth case. I mean, this I think the BB idea maybe not good idea for use this kind of function. So for this kind of special non-smooth functions, you do have to use I mean, the optimization people nowadays is the separate problem into smooth part and the non-smooth part. They use ADMM, this kind of technique, or augmented Lagrange. Then you can always you can handle the smooth case by which is good for smooth. So if you're good to play basketball, you play basketball, you play volleyball. So I don't want to mix you together. So don't want to. So this is the kind of idea. We minimize the function, which is a plus b, have two terms. A is smooth, B is non-smooth, but the symbol of the separable. Then we using like minimize this, use gradient, and minimize this like a shrinking, something like a technique like that, and combine them together. Yeah, good question. I know.
Could I add a small
Yeah.
remark?
Hmm?
Could I add a small remark?
Yeah, sure. Yeah.
Actually,
Yeah.
you have to use hybrid methods.
Yeah.
Because for example, the L1 non-monotone version, eventually your problem is going to become C2 smooth. But not from the beginning. So the beginning you're going to use like parameter splitting or variable first order methods, and then after a certain point you can turn to BB methods if you want. Because actually that's the result that eventually the problem is going to become C2 smooth.
Can you just take a family of smoothing things gradually
It's not
approaching the original function, and each step you just
no, it's
make
not,
it sharper and sharper and so on. And then you just use the gradient method directly
No, it's not.
and control the steps instead.
It's not using some technique to smooth the function. It's that the problem itself gonna become smooth. It's a nature by the function, for example, the L1 node, because you want to find a sparse solution. So eventually, when you find the spot of the sparse solutions, actually only with respect to the spot, the function is you can throw away the absolute value. You can just keep it as the linear function locally around the non-zero values, and this becomes C2 smooth. It's not some approximation. It's just itself is becoming C2 smooth. And then you can use in the smooth optimization method like each step or other methods to do the optimization.
So here, if each must be positive definite.
Yeah.
If not, you have to do something.
Yeah, I mean, if it's not positive, if that will depend on whether you have negative curvature or you have a positive semi-definite. So if you have negative curvature, the method have to adopt it to modify the algorithm to allow you can search along negative curvature direction. Because for people working for convex optimization, they were always saying if you have a long convex problem, which is not good, because convex problem people have polynomial algorithm, people have can have a very fast algorithm and polynomial algorithm and like Lestrov, Stephen Boyd, all these big guys very like convex optimization. But from optimization point of view, from the idea of you trying to minimize the function, actually negative curvature is not a bad guy. Because you have a negative curvature, that means you can reduce the function very quickly. So that means for negative curvature problem, once you have negative curvature, if you can identify your problem, have negative curvature, then you can use negative curvature to reduce the function. You don't care about the theory. If I can reduce my function, why I should be very happy. If you can earn money, if your bank account increase 1 million, you just keep quiet. Something like that. So that is one part of your question about whether you have negative curvature. If you don't have negative curvature, but you're not positive definite, that means you have positive semi-definite. So that means, I think you have a null space of zero argument. So because our group nowadays is really interested in the subspace approach, so you can divide the problem into by subspace technique. In one of the subspace you have a zero eigenvalue, but so which is the function is basically the linear function, because you don't have second term. But in the orthogonal, which is you have zero eigenvalue, and also in the orthogonal space you have positive definite. So that means if you adopted subspace approach, then basically you have in the lower dimension you have a positive definite problem, but you have a zero a low space which is the linear function. So you can decompose the problem. Yeah, good question.
Any more? If not,
Okay. Thank you much indeed.